This video, which is an extension of the lecture, this is not included in the basic program, we are going to review the derivation of some cosmological solutions. These cosmological solutions are solutions of the cosmological Einstein equations, which I think that will be interesting for you, and that you can also take as an example or exercise to which you can apply what we have learned on staticity and spherical symmetry. So the questions that we want to solve are equations in which the energy momentum tensor of matter is set to 0, and here we are adopting the point of view that the cosmological constant is not part of this T mu nu, and we are left with these equations, which are called the cosmological Einstein equations. This is in 4 dimensions as usual. Otherwise you would have a different factor here, a different numerical factor. Okay, remember that a positive lambda is de Sitter like, and a negative lambda is anti-de Sitter like cosmological constant. And well, if you remember what we did when we studied vacuum solutions, first we took the trace, we simplified these equations, and we took the trace, we replaced the value of the Ricci scalar in the original equation, and we derived some simplified equation. Okay, first we take the trace, so this means multiplying this equation by T mu nu, and since T mu nu, capital T mu nu, is R mu nu minus a half G mu nu R, you get R minus a half, and then G mu nu, which is 4 times R plus 4 lambda equal to 0. This gives R minus 2R, so this is minus R, and we arrive to R equal to 4 lambda. Now we can replace this again into the original equation, now without the trace, and you get R mu nu minus a half G mu nu and the value of R, which is 4 lambda, plus lambda G mu nu equal to 0, and you see that this gives you R mu nu equal to lambda G mu nu. And these are the simplified, this is the simplified form of the Einstein equations that we want to solve. The solutions to this equation are called in general Einstein spaces. Okay, geometry, this is the name they are given in geometry. Okay, so we are searching for static spherically symmetric solutions of these equations. We are going to adopt the form of the metric that we used also when we derived the Schwarzschild equation solution, and this is it. And remember that we also have the form of the Ricci tensor. We computed it before, so we are just ready to substitute the value of RTT and so on, and the components of R mu nu and the components of the metric in the equation. Okay, so the TT component of the Ricci scalar is, you can look it up in the lecture notes, it's just this, and the equation tells you that this is lambda GTT, and with our notation, the names that we have chosen, this is lambda lambda. Okay. First I write all of them, and then okay, this is, remember, minus lambda minus 2, RTT plus 2r double prime over r, and this is lambda drr, but this is minus capital lambda divided by lambda. And okay, let's also consider r theta theta, although we, as we discussed in the previous video, this depends on the other two and should not give us anything different. Still, let's write it and then we can check it, because in this case this is easy to do. So it's just this minus 1, and this would be lambda g theta theta, and this is minus lambda r squared. Okay, remember the phi equation is proportional to the theta theta 1. And okay, we can start with the RR equation, but we know that this RTT is just, well, we have it here, it's just lambda lambda. So using that the TT equation in it, we get minus lambda minus 2 capital lambda lambda plus 2 r double prime divided by r equal to minus lambda divided by lambda. And you see that these two terms cancel, and this implies that r double prime is 0, and we said, okay, we can integrate immediately, and we write it in this form. We know that we can eliminate this, well, I don't need parentheses. We know that we can eliminate this constant b by a shift, so we do that. Okay, and we are left with AR, and we choose this IA equal to 1 as normalization condition. This is something that we also did in the case of the Schwarzschild. So now we can go to the TT component itself, and this is minus lambda divided by 2r squared, r squared lambda prime prime equal to capital lambda lambda. Okay, this r squared, it is just r squared. Okay, this lambda in one side and lambda in the other side can be cancelled. This is just r squared, and then we have r squared lambda prime prime equal to minus lambda 2r squared, which is you can integrate immediately. Remember, this is just d of this divided by dr, so we take dr to the other side and we integrate. This gives us immediately this, and this is minus 2 divided by 3 lambda r cubed plus a divided by r squared, and this again can be integrated immediately. This is the lambda dr, so we just multiply all this by dr and we integrate both sides. This gives us lambda equal to minus capital lambda over 3 r squared minus a divided by r plus some other constant that again I call b. Okay, and this is just the solution. Okay, if you want, you can check the theta theta component as an exercise, but this is it. With this b, again, we choose equal to 1 as a normalization. Okay, this is standard, and the solution can be expressed in this form. First is lambda, which is minus a divided by r minus lambda divided by 3 r squared t squared minus the r squared divided by this same expression minus r squared the omega squared. So which solution is this? It's a two-parameter family of solutions. Well, if you consider the cosmological constant as a parameter, otherwise there is just a single parameter, which is a. So let me see what happens if a is 0, and you remember how we constructed the sitter and the sitter space. You will recognize that this is the metric that we constructed as the induced metric of some hyperboloid and embedded in a higher dimensional space and so on. So these are the sitter and anti-de Sitter spaces when a is equal to 0. And there was a parameter which we call the anti-de Sitter or the Sitter radius. And here the thing that plays this role is this lambda over 3. This is the de Sitter or anti-de Sitter radius. Okay, so there is this relation between the cosmological constant and the r squared that appeared in the formula that defined the hyperboloid. As I said, sometimes this r is written as L because it is another length scale. On the other hand, if you see that when lambda is equal to 0, this is just Schwarzschild. And the parameter a corresponds to 2gm, the Schwarzschild radius. Okay, now you could be tempted to say that it must be the same, but although it is the same, this is not so easy to say because this identification was made in the asymptotic regime. Just go to a faraway distance, you measure the Newtonian potential, and you say, okay, this Newtonian potential was produced by this total mass m. Okay, and this is how you identify the value of the constant a. However, if you go to large distances, instead of decreasing, you have this term here that grows. Okay, so it is not so easy. What you can say is that when r is very large, okay, this term is small, and this solution, instead of becoming Minkowski at large distances, becomes de Sitter or anti-de Sitter. This is a behavior that probably you didn't expect and that can be interpreted as follows. Minkowski is, you can view it as a sort of vacuum for the gravitational field. It's the space that corresponds to trivial gravitational field. Then you excite this vacuum, put in masses and so on, and then what you get, if these masses are in a confined region of the space, well, what you get is, for instance, Schwarzschild, and if you are far away from this mass distribution, you recover the vacuum. So asymptotically flat means asymptotically the Minkowski vacuum, and that's the definition, as we said, of an isolated system. If there is a cosmological constant, one thing that you should know is that if lambda is different from 0, okay, in these simple equations, Minkowski is not a solution anymore. of the Einstein equations. So this is, you may think that this is surprising. On the other hand, you see that the de Sitter or anti-de Sitter are solutions. And okay, then maybe the right interpretation would be to think that de Sitter and anti-de Sitter are some other vacua of the gravitational field that replace the Minkowski vacuum when there is a cosmological constant. Indeed, you can think like that, and then the interpretation of this solution would be that there is this de Sitter and anti-de Sitter vacuum, and you perturb it because you put some mass or energy distribution somewhere. Then the solution now, when you go far away from this mass distribution, becomes the vacuum again, which is de Sitter and anti-de Sitter. The piece that you need, the piece of information that you need to arrive to this conclusion could be requires you to think on the meaning of vacuum in the gravitational context. In special relativity and in quantum field theory, in special relativistic quantum field theory, your vacuum is the state of lowest energy. But there is an energy scale that can compare different states of the system. However, in gravity, there is no such a scale. If you have different vacua or different states, de Sitter, anti-de Sitter, say, and Minkowski, there is no way to say that one has more or less energy than the other. That thing doesn't, it's just impossible. What you can say is that, for instance, Schwarzschild has this energy, this much energy or mass. Because then it's a solution which is asymptotically that vacuum, and then you are comparing the energy of that solution with respect to the vacuum. That you can do. But you cannot compare different energies of different vacua and say, okay, out of all these possible vacua, my real vacuum is the one that has less energy. You cannot compare the energies of different vacua that have different asymptotics. So how can you distinguish what is a vacuum or select a vacuum in this gravitational context? This is a very good problem. Okay, I don't think it is has been solved or it is completely understood. There is not a potential that tells you that which is the solution with less energy or less potential energy. So there is nothing like that. You have to think of something else. The fact that you have many solutions with different asymptotics, in fact an infinite number, means that there is a potential infinite number of vacua, and you have to try to find some principle to choose between all of them. In the context of a string theory, in fact this problem is common to all theories in which gravity is present, because this is really a problem of the gravitational interaction understood as an interaction represented by a metric. So it also appears in string theory, and there it has a name. This is the landscape. Okay, the landscape is like is a space of all the possible vacua, but this string landscape is nothing else but the landscape that you have in gravity. It's just that in general relativity the problem is not called in that way, and people have found a principle that leaves some people satisfied. The principle has to do with the symmetry that you have. So people tend to choose vacua as those to call a solution a vacuum if it has the maximal symmetry possible. How much symmetry is that? Okay, Minkowski is one of them, and it is characterized, as you know, by 10 isometries, which is the dimension of the Poincare group in 4 dimensions. Well, this you can prove that in 4 dimensions you cannot have spaces with more than 10 isometries. So other spaces with more than with 10 isometries will also be maximally symmetric. They are called. Okay, so it's Minkowski is maximally symmetric. What are there other maximally symmetric spaces? Well, it's not surprising that there are two. In fact, in any dimension this happens, that there is de Sitter and anti-de Sitter. So this Minkowski, de Sitter, and anti-de Sitter are the three maximally symmetric spaces that you can find in any dimension. They have the maximal number of isometries possible. This means that you can characterize the motion of particles with maximal number of constants of motion and so on. Okay. This is a desirable property, but really, I mean, who knows if this is better than something else. Okay, it's a principle that people have adopted, but I don't think that there is anything much deeper than this. Okay, these are the three. There are no other three, and it's funny that you can find similar solutions, okay, like Schwarzschild, with different asymptotics, because you can think that indeed you can view those solutions as perturbations of those vacuum, Minkowski, de Sitter, or anti-de Sitter. The standard Schwarzschild solution could be a perturbation of the standard Minkowski vacuum. There are other solutions which also are asymptotically flat, like Kerr, and they have an associated de Sitter and anti-de Sitter solution, many other. And this is why I think you should know this.